All right, I had to get my Wi-Fi going here. It's a little finicky in this building at times. Okay, so just a heads up about our next exam. It will likely be approximately 2 weeks from today. I need to take a closer look at how things will schedule out, but we have this chapter on integration and then the corresponding problem set. Get that handed in, get it back to you. So I think we can do all that in 2 weeks. So to have an exam in 2 weeks from today, but we'll double check on that. So I'm just trying to give you roughly a 2-week warning. Yes, and a week from today is, oh, you're right. But that should not affect anything. That's a good point, but that won't affect this because actually it comes at a good time because we'll finish integration on Tuesday. You'll have your COVID day. You can get your homeworks done, turn it in on Friday. So yeah, you're right. Thank you for reminding me that. That is correct. But that's should actually be a good timing for us with this. All right, so I'll let you know for sure, but plan on 2 weeks from today. What date is that? 15, 16, 15, correct. Oh, tax day. Oh no, they moved that back to May, so we're fine. Yeah, so we'll plan on the 15th. We'll see how things play out. All right, so we're looking at any other questions about anything before we get rolling here? Sweet. I assume you're talking about the COVID day, not the exam, as far as being sweet. Okay, so we're talking about integration, and I just reminded you from calculus class what integration means. So a definite integral, in this case, a function f of x, integrating with respect to x from a to b, is just the area under the f of x curve between a and b. Yippee. So conceptually, it's very easy to think about how we could devise ways to calculate, approximate an integral. And so all of this is very intuitive. It's easy to picture in our minds. And then last time we did the calculus-y formal definition with the limit of delta x going to 0 of the integral. Now we're going to look at how we can approximate this. So we'll do a similar thing for the derivative. We'll start with the formal definition from calculus of the derivative, and that'll help motivate how we could approximate the derivative. So the same idea here. We could say, okay, fine. The integral is the area under the curve f of x, and we could approximate that as delta x times the sum of all the f's at each of the points. And what that would be doing is approximating the area under the curve as a whole bunch of little rectangles, as I'll draw here in a second. So we have n subintervals, so therefore capital N plus 1 points in our interval from A to B. So it'd be very simply, it would look something like this. Here's my, oops, that's x. And I have my function. And then we start with A, x is equal to A. And we end with x is equal to B. And then in between, we just have a whole bunch of little slivers. So these slivers, according to 7.1, would be little rectangles, because it's going to be the height, f at xi, times delta x being the width of each of our little vertical slivers. And then if you add up these areas, you'll get an approximation for the integral. Okay, so that's fine. Very simple, very straightforward. The smaller the delta x is, the larger the number of intervals n is, and the more accurate the estimate for the integral becomes. So that's fine. It's not a terribly accurate approach, but conceptually, it's a good starting point for us to think about. So there's basically two approaches. One would be to say, well, we already know how to do curve fitting. So if I have a series of points, like this, why not first fit a curve to that and then do our integration to get the area under this curve? So that would be a way that would use the basic machinery that we already have in place. So take the data points, fit a curve, and then integrate that f of x from a to b using our usual calculus techniques. Another approach, which is the approach that we will take, will be to use those points directly, the data points directly, in our integration. So I have points like this, say, and now we're going to connect the dots in some way. Right now I'm just using straight lines to keep it simple. And then we'll get the area under the curve based on those actual data points. So we're going to integrate the discrete points directly with prescribed functions used between the data points. So as I've drawn it, there are straight lines between the data points, but we can use other functions as well. So this is called, or is referred to as using Newton-Cotes formulas. And this is the focus of what we're going to do. So the real question is, these points are given. That's the actual data that we measured. Those are the pressure measurements on our airfoil, for example. And the only question is, are we going to use straight lines? Or are we going to use parabolas? Are we going to use some other higher order polynomial to handle the fit, the curve, sorry, not the fit, but the curve between each pair or 3 or 4, whatever number of points. And we'll start with simple, we'll start with straight lines, and then we'll work our way up and see kind of where things go from there. Now within that, there are two possibilities. So within the second of those approaches, there are two possibilities. The first is what's called a closed method. And this is where the endpoints coincide with A and B. So in other words, I have my function and A and B coincide with two of my points. So I have 2 points, one at A, one at B. I might have a whole bunch in between. Here I've only shown one, but I have points that are exactly at the limits of integration, A and B. That's called a closed method. Similarly then, an open method is where the endpoints do not coincide. So in other words, there's no reason why my limits of integration have to coincide exactly with the location of my data points. So if A and B do not coincide with any of these data points, then we call that an open method. We are going to primarily focus on closed methods. It's not really a big deal to generalize for open methods, but just to keep things simple, we'll focus our attention on closed methods. Okay, so let's think about these Newton-Cotes integration formulas. There's several of them. Again, we'll start with the easiest and work our way up. Each one will get a little better in terms of accuracy, but also a little bit, it'll also increase complexity as well. So let's think about why this is helpful or necessary. So let's kind of zoom in on just a piece of my previous approximation. Remember, the previous approximation said, let me take 2 points. This is f of xi, and this is f of xi plus 1. And this is delta x wide. I've zoomed in, so now it looks bigger. And so this is our curve f of x, obviously. So the idea is, if I just take rectangular shaped slivers, and I get this area here for this rectangle, I'm going to call that I sub I, big I sub little I. So that's the area of one of those little slivers. And you can see, now that I've zoomed in, you can see what's going to happen. It's always going to be wrong by this amount. So this little area up here is not accounted for. In other words, when I add up the areas of my little slivers, rectangular slivers, in my kind of naive approach to numerical integration, I see that I'm always going to be missing those little pieces at the top above the rectangle. Once again, as I decrease delta x, therefore increase the number of slivers, those areas that are not being accounted for will get smaller and smaller and will get more and more accurate. But it's always wrong by that amount. That's not great. So the simple thing to do, I'm not going to actually draw it on the figure, but just to kind of show you where we're headed. So a simple improvement is to say, well, rather than just taking this value as a constant and therefore giving me a rectangle, let me draw a straight line between these 2 points, and then I have a trapezoid. And that should be more accurate than using rectangles. So we'll do that first. That's called the trapezoid rule. And then we'll notice, okay, we're still missing this piece right here, this area right here. So then you say, well, why not use a quadratic or a parabola in between? So a second order polynomial instead of a first order polynomial. And that will get even better, but a little bit more complicated. So that's the route we're going to take first. You'll see how each of these play out. So basically, that's the idea. These various Newton-Cotes formulas correspond to using different order polynomials in order to approximate our function f of x between the given data points. Remember, I don't actually have this function. I just have these data points. So I want the approximation or the function I'm using, the Newton-Cotes formula that I'm using in between these points, to be such that it can be as close to the actual f of x as possible in order to improve the accuracy. So that's where we'll be heading. Now, just some notation. So I is the total integral from a to b. We're going to break that up into the integrals of each of the little pieces. So from x1, which is a, to x2, and then x2 to x3, x3 to x4, all the way to the end. The last sliver is xn to xn plus 1. And xn plus 1 is the right boundary b. So each one of these integrals is the area of this piece right here. So whether it's a rectangle, whether it's a trapezoid or something else, it's going to represent that angle. So that's why I called it I sub little I. And then we simply add up those little areas for all of the slivers from A to B. So little I goes from 1 to capital N. And we add up all of those I sub i's. Each I sub I, this is I sub 1, I sub 2, I sub n, and add them all up. If I look at just one of these segments, so I sub little I, sounds like I'm saying I spy little I. So each one of those little slivers then is the area under the curve from xi to xi plus 1. So I is from xi to xi plus 1. And then that is going to be approximated by some representation of the actual function. So f of x is the actual function, and f sub I of x is going to be the function that I use to represent or approximate that actual function. So you see that here, f of I x is a local representation of f of x just in this little interval. And then each little interval has its own fix, f1, f2, f3, all the way down the line from A to B. All right, so relatively straightforward conceptually. Now let's see how we can actually do this and what we get when we do the integration. So first is the trapezoid rule, named that for the reasons I just stated a moment ago. We're going to use a linear approximation. It just goes from one side to the other. So our f sub I of x between each adjacent point is going to be a straight line. So we're just literally, this is like the linear spline that we had a while back, just straight lines between each of the points, add up the little slivers, which are trapezoidal shaped between each of the points. So that will allow us to have each little delta x segment, rather than being a rectangle, it'll be, of course, a trapezoid, which is what gives it its name. So it's going to look like this. So let's say our function now looks like this. Here's the fxi point. Here is the fxi plus 1 point. And rather than just going zippity zippity horizontally across like that, we're now going to go zippity zippity straight line from 1 point. Oh, it made it straight, nice. So 1 point to the next. And then this becomes the area I sub I. Once again, this is our delta x. So we've zoomed in, so the width of this little sliver is our delta x. And let's make a delta xi. There's no reason why it has to be the same. So now you'll see that this is the area that's not accounted for. But that's smaller than it would have been if we just went straight across like this. So we've improved it by this amount, this triangular area. We're still not exactly right. We still have this part that's missing, but now we have this part, which is indeed being included. So it is better. It's not perfect, but it's better. Now, I know even I can remember the area of a trapezoid. So let's just write it down based on what we know about trapezoids, and then we'll derive it. So, and I'm going to derive it. We'll get, of course, the same thing, but I'm going to derive it so that we can see what the approach is. So when we do Simpson's rules, then for more complicated shapes, we'll see what the procedure is. It'll make a little more sense. But I know the result, the area of a trapezoid, so I sub I, is just the average of these two heights times the width delta xi, right? So that's the area of a trapezoid. And then you'll just add all those up across the entire interval from A to B. Once again, that is the answer. It is correct, but let's formally derive it in order to see how we do this in a more general way. Okay, so I write down a general form of a straight line between each pair of points. So f sub I of x is a0 plus a1 times quantity x minus xi. So that's a straight line between 2 points in the xf plane. If I determine the a0 and a1 constants, coefficients, then I get this. And that is simply the equation of the line, this line right here, that goes between those 2 points. That's all I've done. Just good old fashioned algebra. So f sub I of x, which is the shape in between this straight line, is the value of f of xi, that's at the left side of the sliver, plus f sub x sub I plus 1, that's the value on the right, minus the value on the left, divided by the distance between them, times x minus xi. That is the equation for that straight line. And you can confirm that. There's nothing terribly exciting about that. Okay, so given that, let's now integrate. So let's just take one little sliver, big I sub little I. So x sub I to xi plus 1 of f sub I of x dx. I just determine what f sub I of x is. That's this thing here in square brackets, exactly the same thing in square brackets. We integrate with respect to x. These numbers are all constants. The only non-constant value is this x. Everything else I know. I know the locations of my data points, the xi's. I know the widths of my little vertical slivers, delta xi, and I know the values of f at xi and xi plus 1. Those are from my data points. So I know everything in here except for this x. That's the only variable. So if I integrate a constant with respect to x, that's just the constant times x. If I integrate a constant times x, I get the constant times x squared over 2. Then I put in the limits of integration. So xi plus 1 first, so x becomes xi, and this x becomes xi plus 1. So the xi plus 1 minus xi, well, that's just delta x sub I. And then I put in the lower limit, x sub I, so I have an f of x sub I times x sub I. That's this right here. So substituting this into here gives me this. When I substitute this into here, I get xi minus xi, which of course is 0. So that term vanishes at the lower limit. So the thing in square brackets is from applying the square brackets at x sub I plus 1. And this is from applying the thing in square brackets at x sub I to get that. Then a little bit of algebra. So you have an f of xi times xi plus 1 here. You have a minus f xi times xi there. So I can put these two together, and that's just f sub xi times delta x sub I, because x sub I is x sub I plus 1 minus x sub I. Boy, never thought I'd say sub I so many times. And then we have the 1/2 of this. So 1/2 of x sub I plus 1 minus f of xi. And I see that I've missed a parenthesis there. And then one of these cancels with this. And that gives me the delta xi from this term out here. Everybody following okay? This is the easy one. Simpson's rule gets a little bit more hairy. It's the same process, but it's a higher order polynomial, so it's a little bit more messy. Okay, so what does this give us? Well, now I have an f of xi minus f of xi. Actually, sorry, half of xi. So that is a positive half of xi, that's here, plus a half times f sub I, f sub x sub I, f of x sub I plus 1, yikes, which is here, all times delta x sub I, which with all that sub I-ing all the way, well, that looks familiar. That's what I assumed it was going to be based on our known area of a trapezoid in the beginning. So fine, that is an expression for the area of one of our little vertical slivers that has a trapezoidal shape, a straight line across the top. The sides are always going to be vertical straight lines, and then it's just a matter of what we do at the top. Right now, first we used a horizontal line, Now we're using a straight line between the 2 points, and then we're going to use a parabola between those 2 points. Phew, that seemed harder than it needed to be. So then you just add them all up. So the total area under the curve f of x from A to B is just the sum of all these little capital I sub i's. And so you just add them up. It's the 1/2 times the delta x sub I times the quantity f of x sub I plus f of x sub I plus 1. And you just calculate those. Add them up, and you got an approximation for, it is an approximation, it's not exact, for the total area under the curve I. You'll notice that I've been careful to allow for the delta x's to be different. For trapezoid rule, there's no reason why the points have to be equally spaced. And that's actually one of its advantages. So whatever the data is, if the data is equally spaced, fine, you can use trapezoid method. But even if they're not equally spaced, then you can still use trapezoid, whatever the delta x's are, doesn't matter. So that gives the maximum of flexibility. The approximation improves, of course, as your delta x's get smaller, which corresponds to n getting bigger. So you have more of these little vertical slivers to add up. There is an example in the Python tutorial showing how to do the trapezoid method in Python. All right, let's do an example. I want to show you, before I do anything else, I want to show you how actually quite easy this is. It's not difficult to do. It seems confusing. It is somewhat tedious. That's why we have a computer doing it, but it's really, really not that difficult. So we have an integral of sine x. I want to integrate from 0 to pi over 2. And I'm only going to use n is equal to 2. So that means there's going to be 3 points and 2 intervals. So it's going to look like this. So I have a point at x1 is equal to a, which is equal to 0. We'll have 1 in the middle. That'll be x2 is pi over 4. And then at the end, that's going to be x3 is equal to b is equal to pi over 2. So I want to approximate this area right here using just 2 intervals with the trapezoid method. So that means there'll be straight lines between these 2 pairs of points. Obviously, integrating sine x is easy analytically, so we can get the exact solution and compare it and see how well we've done. Okay, so let's first do the trapezoid method. And I'm only going to use n is equal to 2 to minimize the tediousness somewhat. Obviously, the larger n is, the more tediousness we have. So my I is approximated as 1/2 times the sum from I is equal to 1 to capital N is 2, of f of x sub I plus f of x sub I plus 1 times delta x. That's straight from right here. That's this expression right here. Okay, so let's just apply that to our particular situation. Well, I'm going to bring the delta x to the front, so delta x over 2. And then I'm going to write out the sum. So I have 2 terms in the sum, so let me write both terms out. So I have f of x1 plus f of x2. That's for I is equal to 1. And then for I is equal to 2, I have f of x2 plus f of x3. Okay, so that's just this expression here in square brackets for I is equal to 1 and I is equal to 2, corresponding to our summation. It's a little chilly for opening day, huh? Cubs are at home. Sox were smart. They're playing in Southern California, so that was smart. I'm always amazed at how green they can get the grass in these stadiums in early April. I don't know if they do this here, but I know in Europe, because they play soccer through the winter, and the grass always looks amazing. So if you go into one of these stadiums during a non-game day, you'll notice what they actually do is they have these giant, they look like bridges that span the entire width of the field, and they just have lights. And then they just wheel it down very, very slowly. So it's always shining light on the grass. And of course, they're watering it all the time. So it's got plenty of sun, plenty of water. Some of them even have heating systems underneath that keep it nice and toasty warm. Because, you know, you wouldn't want those Spanish players when they fall on the turf and roll 10 or 12 times. You wouldn't want them to actually get hurt, because if they actually got hurt, then we wouldn't be able to make fun of them for pretending like they're hurt. Why do Spanish players do that? No one else. So actually the turf that's used in Lambeau Field, if you compare Lambeau Field to Soldier Field, you'll notice a big difference. So in Soldier Field, they usually have to replace the grass once during the season, sometimes even twice. If they make the playoffs, sometimes even a third time. Sometimes they just do like down the middle of the field, which is the most damaged and heavily trafficked. And then you go to Green Bay, of course, who always goes to the playoffs every year. And you notice they never have to redo their turf. What's so special about grass in Green Bay? Well, it turns out that the grass in Green Bay, you think it's real, right? Well, some of it is. So they have this special turf. I can't remember the name. They use this in some of the stadiums in Europe for soccer, which is why their grass can hold up so well, even during the winter time. It's kind of a foundation of fake grass that has a lot of things that the real grass roots can kind of hold on to. And then they plant real grass in amongst the plastic grass, and you can't see the difference. So the plastic grass kind of holds together the real grass. So it looks like, and it feels like, and it plays like real grass, but they've kind of tricked the real grass into, not getting chunked away from cleats and things. It's pretty ingenious. It's extremely expensive, which is why the Bears won't use it, apparently. They do that at indoor baseball stadiums. Yeah. So then, do you know what they do for the Arizona Cardinals stadium? So they have a dome. They can open it. They can close it. It has real grass. So you're thinking, wait a second, you can't have real grass in a dome. It needs rain and sunlight. Yeah. So you know what they do? They slide it out into the parking lot outside the stadium. Let it grow in the beautiful Arizona sunshine. No rain, of course, but sunshine. And then for games, they slide it underneath the seats back into place. It's a pretty ingenious. If they use real grass, like at Miller Park, if they roll the grass out, no, yeah, exactly. So we've come up with all kinds of crazy ways to get real grass into stadiums. When I was growing up in the turf was just sort of kind of becoming popular, but it was nothing like what they have today. So most turf fields that you see, even in NFL stadiums, but they use a very similar type in college and even high school stadiums now, oftentimes, because the prices come down significantly. It's modern stuff is kind of this rubberized. In fact, if you see someone slide or get tackled, you often see kind of this black cloud come up. Those are tiny little rubber particles. They use old tires and ground up the rubber. So it's nice and soft and bouncy. the original turf fields. Have you ever been to your grandparents' house? And because your parents would never do this, I hope. But in your grandparents' house where they had that green carpety kinds of outdoor carpety stuff, sometimes on their stairs or their front or back porch, you know, so outside. And it's just horrible. It just feels terribly fake and certainly uncomfortable to get tackled on. Well, that's essentially what the original turf fields were. It was concrete. I mean, this is just unbelievable to think about today. It was concrete base, and then they would just basically put this thin layer of green plastic over top, and it was ridiculous. I didn't play football, but I was in the band, and so we used to march on some of these fields, and it was just your feet would get creamed marching on this hard concrete surface barely covered with grass. So we've come a long way. We have a lot more interesting options, and I don't remember why that even came up. Oh, because of the weather and opening day. That's why. Okay, back to our regularly scheduled program. So this is for I is equal to 1. And this is for I is equal to 2. We'd have one of these for each of our i's. If we had 23 i's, we'd have 23 of these. Okay, great. So let's then put in the values of f of x1, f of x2, and f of x3. Actually, because we have two f of x2s, let's combine them first. So this will be delta x over 2 times the quantity f of x1 plus 2 f of x2s plus f of x3, just to make things a little bit simpler for us. Okay, great. So we've combined those. Now, let's put in the actual values for this particular f. So we have our delta x over 2. Actually, since we're putting in values, let's put in delta x over 2. So let's see what it was. So it goes from 0 to pi over 2. So each delta x is pi over 4. So we have 1/2 times pi over 4. That's our delta x. And then let's put in f of x1. So what's f of x1? Well, that's sine of x1, but x1 is just 0. So that's 0, sine of 0 is 0. Plus 2 times f of x2. Well, x2 is pi over 4, correct? Yeah. So this is 2 sine pi over 4, okay? Plus f of x3, x3 is pi over 2, so this is sine of pi over 2. I told you it was tedious. We only have n is equal to 2. So the first term is gone. So this is pi over 8. And then the following two terms, we have 2 times sine of pi over 4 is root 2 over 2. And then sine of pi over 2, that's just 1. So the 2's cancel, and we have pi over 8 times the square root of 2 plus 1. And if you calculate what that is, that's about 0.9481. Okay, that's the exact value, but numerical value for comparison with the exact solution. So that's it. That's the trapezoid rule. And all you're doing is adding up the areas of each of the slivers, but it looks like that you're just combining these f of x's in kind of a strange way. Okay, so 0.9481. Now let's get the exact solution. I have the integral from 0 to pi over 2 of sine x dx. Okay, integral of sine x dx is minus cosine x, and then from 0 to pi over 2. So that's minus cosine of pi over 2. Why am I cramming it all over here? So that's equal to minus cosine of pi over 2 plus cosine of 0 But cosine of pi over 2, that's 0, right? Yeah. So that's 0. Cosine of 0 is 1. So I, the exact value, is 1. Our approximate value was 0.9481. So we're only off by 5.1%. And that's with only n is equal to 2. Obviously, if I had more n's, more slivers, larger n, then that would get smaller, or the error would be smaller. The solution, the approximate solution would be even better. So that's pretty good, especially for only 2 intervals. Okay, normally, of course, we can't get the exact solution. That's why we're doing it numerically. But in this case, we can, so we can compare. And we'll come back and do the same problem using the Simpson method, which is what we'll discuss next. Any questions about the trapezoid rule? This is about as pluggy-chuggy as this class gets. Derive the formula, use the formula, and you're done. Okay, the next method is called Simpson's 1/3 rule. There are various Simpson's rules. The 1/3 references the coefficient out front, as you'll see very shortly. And then there's a Simpson's 3/8 rule, which comes from a different approximation. The idea behind Simpson's 1/3 is, instead of using a straight line between our 2 points that bound our intervals, we're going to use a quadratic approximation, or a parabola. So the f of x between 2 points, actually not 2, because we're going to span 2 intervals for reasons you'll see in a second. So the function is going to be assumed to be, or approximated by, a quadratic. Now, in principle, it should be better than a straight line, just like polynomial interpolation of higher order is better than polynomial interpolation of lower order. Now, we're going to need 3 points in order to define this quadratic, because a quadratic, from the straight line, we had 2 constants to determine. We had 2 unknown constants to determine. Now we're going to have 3, because we're going to have a second order polynomial. So we have a 0th order polynomial term, a 1st order polynomial term, and a 2nd order quadratic order polynomial term. So we actually need now 3 points so that we have the 3 constants that we need. So it's going to look like this now. So here's my function. Here's xi plus 1, and then xi plus 2. So we're going to take 2 adjacent intervals, so 2 adjacent slivers, each with the width of delta x. So as I'll emphasize in a moment, the delta, well, actually it's right here. The delta x's do have to be constant now. They can't vary from one sliver to the next. And then these values, this is f of xi. This is f of xi plus 1. And this is f of xi plus 2. Great. So rather than, the main thing is, rather than 2 adjacent points and 1 sliver, it's going to be 3 adjacent points and 2 slivers. And that's just going to be so we can get enough equations to solve for the coefficients. So this is now going to require an odd number of points, which means an even number of intervals. So n has to be even now, because each of these pieces is now going to span 2 intervals rather than just 1. So n has to be even, and then n plus 1, of course, then is odd. All right. So now let's write down our general form of the quadratic, which is just a parabola, and that's right here. So that is f of x, f sub I of x. That is the approximating function. It's not the real f of x. It's an approximation of f of x between x sub I and x sub I plus 2. Once again, one function spanning two adjacent intervals. Here is our generic second order polynomial, C0 plus C1 times x minus x1 plus C2 times the square of x minus xi. I think I said x1 instead of xi. And so now we have three coefficients that need to be determined. To determine those coefficients, we're going to impose three conditions, all of which make sense. So f sub I of x sub I is the value of f of x sub I. Same thing at I plus 1, same thing at I plus 2. All that's saying is, I don't know what's going on in between the points, but it has to go through these 3 points. So this is like an interpolating polynomial that we had earlier. Has to go exactly through those 3 points. So the approximating function has to match up with the actual function at those 3 points. That's what we're saying. All right, then you go through the same process. I won't bore you with the algebra. It's just more of the same. It looks just like this. The difference is, rather than putting in this thing in square brackets for f sub I of x, we're now putting in this mess. Then you do the integration, put in the limits of integration, simplify things down as much as you possibly can algebraically, and you get this expression right here. So the first two things you'll notice is, instead of a 1/2 out front, we now have a 1/3, thus Simpson's 1/3 rule. The other thing you'll notice is, rather than two values, f of xi and f of xi plus 1 inside, we now have 3 values. And this 4, the 1, and the 4 come from the result of this integration. So that's very similar to the previous case, trapezoid rule, just more stuff to integrate. Gets a little bit messier. And now the I is actually skipping every other point. So it's all the odd points, 1, 3, 5, 7, 9, because when I is equal to 1, this is going to use the I is equal to 1 sliver and the I is equal to 2 sliver, which goes from 1 to 3. And then the next one will be the next 2 slivers. So 1 to 3, 3 to 5, 5 to 7. So that's why this is skipping every other point like that. Okay. So if I sum over the entire interval, so here is my Simpson's 1/3 rule from 1 to 3. Here it is from 3 to 5, and then 5 to 7, 7 to 9, and on until you get to the last 2 intervals, which is capital N minus 1 to capital N plus 1. And then you add all of those up. And when you do that, you'll see that there's only one x1, so f of x1. There's only one of the last point, f of x sub n plus 1. So there's only one of those. But there are 4 of the even numbered points. So I goes from 2 to 4 to 6 to 8. All the even numbers has a 4 coefficient out front. And all of the odd numbered points have a coefficient of 2. Because here's an x3, here's an x3. Here's an x5, the next one will have an x5. Up to the last 2, here's an x sub n minus 1. The second to last one will have an f of x sub n minus 1. So there's 2 of all the odd ones, 4 of the even ones, 2 of the odd ones. And then that's our formula. And then we use that instead of the trapezoid rule. Once again, it involves 1, 2, 3, 4 now instead of 3 points. But nevertheless, a little more work, but nevertheless, that is the result that we get. Okay, so let's do our example again. Same one, sine of x from 0 to pi over 2. we'll use n is equal to 2, so it's an apples for apples comparison, but now using the Simpson's 1/3 rule instead of the trapezoid rule. So now it's going to look like this. I is going to be approximated as 1/3 of delta x, which is pi over 4, same as before, times f of 0 plus 4 times f of pi over 4 plus f of pi over 2. I only have to apply one of these. So even though capital N is 2, we span, our one application of Simpson's 1/3 rule spans every other interval. So the 2 intervals that we have are all included in this one summation. And then we can put in the values, which we had before, same as before. So this will be pi over 12 times sine of 0 plus 4 times sine over pi over 4 plus sine of pi over 2. This, of course, again is 0. Sine of 0 is 0. Sine of pi over 4 is root 2 over 2. So this is then equal to pi over 12 times 4 root 2 over 2. And then sine pi over 2 is 1. And so you calculate that with your calculator, that's 1.0023. And you can see that's better. The exact solution is 1. So you can see now we only actually have 0.2% error with n is equal to 2. So clearly it's better, at least for this sine function. It's always better, but it's significantly better. We went from 5-point-something% to 0.2%. So that's very nice. That is Simpson's 1/3 rule. Okay, some comments. As I said, requires an odd number of points, therefore an even number of equally spaced intervals n. So that's the 2 limitations. The big one is that the delta x's have to all be the same. I can't have different delta x's. So my data points have to be equally spaced, and I need to have an even number of those points. Sorry, an odd number of the points, so I have an even number of the intervals. It is more accurate than the trapezoid method. That's why we talk about it and use it when appropriate. And that's just simply because we're using a higher order polynomial to approximate the function between the data points. There is a Simpson's 3/8 rule if you use cubic polynomials. So we used constants, we used linear functions, that was the trapezoid rule. Then we used parabolas, quadratics, that was the Simpson's 1/3 rule. If you use a cubic, then you need 3 intervals, and it'll be more accurate because it'll be a cubic, but you have the additional calculation and limitations on the n. So now the number of n's would have to be some multiple of 3, integer multiple of 3. As I said before, you can get similar open formulas. These are all closed formulas, which assumes that the points line up and coincide with our x is equal to a and x equal to b limits of integration. The open formulas do not have that limitation, but again, you get them the same way. You can find them in books, and there's equivalent trapezoid method, Simpson's 1/3, Simpson's 3/8 methods for open formulas. It's open season on open formulas. What if you have multiple integrals? So multi-dimensional integrals. Well, that's a good question. I'm glad you asked. So let's say we have a 2-dimensional integral, f of x, y. It's our 2-dimensional function, and we want to integrate over some range in x and some range in y. So x goes from a to b, and y goes from c to d. It's actually quite simple. All you do, I mean, it's a lot more computation, but conceptually it's quite simple. So all you do is you just first do all these x integrals. So just break those out. And those we've already shown how to do. F of x, y, dx. That's a new sound I've never heard before in my ear. Speaking of sounds in my ear, so I missed you all last Thursday, a week ago, because I got my first COVID shot, vaccine shot on the Wednesday before. I wasn't necessarily expecting to have issues after the first shot. From what I've heard, most people, if they do have issues, which many people don't, they often have them after the second shot. So, but I was prepared. I thought, I'm an old fart, not terribly healthy. I'm sure something bad will happen. So sure enough, wake up Thursday morning, but it turns out, if you read about the side effects of these vaccines, I think I had every single one of them over the course of a few days. By far, Thursday was my worst day. The other days were, you know, I wasn't 100%, but it wasn't bad. I had headaches. I had achiness all over my body. I had chills. I had, of course, tenderness in my arm where I got the shot. I had pain when I would raise my arm. Okay, so that's all. Yeah, it's an inconvenience. Then one morning I wake up and I'm in the shower. I'm like, why are what's that tenderness under my arm? So some people, their lymph nodes. Like, there you go. Then Saturday morning, I forget what I was doing. I remember I was in the kitchen and can't remember exactly what I was doing. And I asked my, did you hear that one of the side effects of these vaccines is ringing in your ears? She says, yeah, I just read that yesterday. Because I have ringing in my ears right now. I literally had every single side effect known to mankind. So I'm a freak of nature. Hopefully that means I will get 0 side effects after my second shot. Still highly recommend it. Absolutely no reason to avoid it. The fun thing about, I shouldn't say the fun thing. The thing that makes being sick okay when it's the result of a vaccine is, you know, you're not really sick. Because normally when you feel kind of flu-y, you don't feel that great, you're like, well, I should stay away from everyone else. I don't want to get anybody else sick. Maybe I'm contagious. But when it's from a vaccine, you're like, kiss me, honey. I'm not contagious. Anyway, that was a little TMI. Anyway, so ringing in the ears. Yeah, because I'm getting weird sounds in my earbuds. Anyway, okay, so you just do the integral in x in the way that we just described. You have to do a whole bunch of them. And then you just integrate with respect to y in exactly the same way. So it's just a whole lot more of the same. So you do the integral in x, then you embed that in here, and then you do the integral in y. So there's really no problem conceptually. Now, again, from an implementation point of view on a computer, there's quite a bit to think about there, but conceptually, it's very straightforward. Siri not available. I'm very sorry to hear that. Okay, great. We have time to start on Gauss Quadrature. We won't quite finish it, but we can at least get started. So this is a very different approach than the Newton-Cotes integration formulas. It has a different mission in life. So it's being done for a different context. So it is a very different approach to doing the same thing, doing this numerical integration. So let me explain all that. So in our Newton-Cotes formulas, we were assuming that we knew f of x at fixed points in the domain. So we imagined that we had this data, we had the pressure measurements along the surface of the airfoil at various increments around the surface. So I have the data and I know where that data came from, what the values of x are for that data. So the values of x are fixed. These points, of course, correspond to the discrete values that we have the data at. So that all makes sense. So I know from whatever experimental or numerical solutions or measurements that I have, where I have the data, what the values of f are at each of the xi's, and I know where the xi's are. because these points are fixed, in other words, because I know where the xi's are, the only way the accuracy of the numerical approximation for integration can be improved is to increase the order of our approximating polynomial, as you saw, from 0th order, 1st order, quadratic, and I referenced cubic, although we didn't do it. That's the only way to improve the accuracy of the approximation of the integral. In certain situations, we can take a very different approach. Say instead, I want to numerically integrate some known function. And you say, well, why would I ever want to do that? If I know the function, I can just integrate it because we love calculus and I love doing integrals. Well, some of them might be hard. Maybe some of them aren't in the back of the calculus book, or maybe it's just a really big problem and we don't want to do it by hand. I want to have a computer do it, or because it's embedded as a part of another numerical method like finite element method. So in finite element methods, you're doing numerical integration all the time. However, you know the functions. They're called shape functions. You know the functions themselves, and you can pick the points where you want to use as references for the integration. There are two approaches for this. One's called Romberg integration. It's based on Richardson extrapolation. We're not going to cover that, but I just want to mention it so if you ever see it, you know where it kind of fits into this whole picture. We're going to use the more common approach, which is based on Gauss Quadrature. So we're going to use Gauss Quadrature. It's a very simple concept, but it's completely opposite to what we just did for the Newton-Cotes formulas. So now what we're going to do is choose the locations of these points, these xi points that we use for the integration based on some smart idea. They're called Gauss points, or sometimes people call them Gauss-Lobato points. Not lobotomy points, but Gauss-Lobato points. So now, rather than these xi's being fixed and known as inputs in a sense into the problem, now we're going to take them as unknowns to be calculated as part of the problem. So here's the idea. So let's think about the trapezoid rule just to motivate this basic idea. So for the trapezoid rule, here's my function for just one little sliver. Say it looks like this. So this is xi, this is xi plus 1. And then for trapezoid rule, I just do a straight line between those 2 points, between f of xi and f of xi plus 1. Great. Then this area is what I get when I do the trapezoid rule. Fine, that's nothing new. It's exactly what we did before. Of course, what you'll see is we're missing this entire area up here. So look what happens if I allow myself to move the xi plus 1 points to another location. So I'm going to pick this location in just such a way so that when I integrate this function, it actually does so exactly. So this is the same function. It's supposed to be the same function. But now, and here are my limits of integration, same as before for that sliver. But now I'm going to pick my points such that when I draw a straight line between them, look what happens. This is x0, this is x1. Here's A and B, say. Now, because I can pick these locations, these x points to be wherever I want, so I can move them back and forth along my curve. Now I can pick them such that this area here exactly balances these areas. And I now, because x0 and x1 are free to be moved, I can pick them such that I can use that as the criteria such that that is the case. And in fact, then I would get the exact value for the integral, which is now this region. So the main difference now is I have a little bit of a positive contribution here and here that offsets this negative contribution, so that I can now get a more accurate value of the integral. But the only way I can do that is if I have the freedom to move the x0 and x1 points, the Gauss points, to some other location in my interval. We'll do this to minimize the error. Sometimes that minimum error will actually be 0, as I alluded to. But in any case, we'll choose it in order to minimize the error. I can also have different numbers of Gauss points. If I increase the number of Gauss points, I can increase the accuracy of the approximation of the integral. So I have full freedom now to choose the locations of the Gauss points and the number of Gauss points I want to use. If I start the problem with my discrete experimental or numerical data at known points, I'm stuck with those. And there's nothing I can do apart from curve fitting and interpolation and some other stuff. There's nothing I can do to change them. So in this respect, in this context, I now have a known function. So to get the integral right, I had the freedom to move the Gauss points in order to get a better approximation. All right, let's rederive the trapezoid method. So we'll get the same result as we did before, but I'm now going to rederive it using the techniques that we will use for Gauss points. You know what, I'm not going to get through all this, so I don't want to start. I can get through the trapezoid rule, but then it's going to not be till Tuesday till I apply the same technique. So I'm going to stop there. Any questions thus far about anything? So again, exam nominally in 2 weeks. I'll let you know for sure soon. And it will be on the material since the last exam, including this material on numerical integration. So what is that? What do we cover? We've covered curve fitting was on the previous exam, then root finding, optimization, and numerical integration. Those would be the 3 topics on the second exam. Okay, they roll, blah, blah, blah. What's the chances we can get the homework due on Saturday? For this week? That's fine. I will change the due date. Oh yeah, tomorrow's Good Friday. What a cruel professor to give a homework due on 11:59 on Good Friday. Okay, I will change that to, and I'll send out an email to confirm it for everybody. I'll change it to Saturday at 11:59, when Jesus was in the tomb. I don't know if that's better or worse. All right, so I'll see you on Tuesday. I will change this phrase. I will change the due date on Blackboard, and I will send out an email accordingly. You ask,